All right, so welcome to the second lecture. So first let me start with some guest administrivia. I hope you've noticed I've been posting material under the resources tab of the Piazza website. In particular, there are last lecture slides. There's also a link to a playlist with the recorded lecture from last time. Also have been updating so the upcoming syllabus on the course webpage, also linked from the resources webpage of Piazza. Right, so we did have a volunteer for scribing the first lecture. I'll later need one also for this lecture. And I've yet to get around to putting down a calendar so you can plan ahead for which lecture you would like to scribe. I'll try to put out a problem set later this week. Remember, it's a graduate seminar, so there may or may not be a cadence to the problem sets, so they will be published precisely when I have time. So I'm not going to commit in advance to how often and with what length. But I do have some exercises that I've put together for the first few lectures, so I'll try to put it up later this week. Okay, so great. So let's get started here. And as usual, feel free to either mute yourself or write in chat for any questions. So as a recap, last time we looked at the notion of mathematical proofs. We saw how to extend them to the notion of interactive proofs. We saw an example of interactive proof for graph non-isomorphism, for which we do not have classical mathematical proofs. So that's interesting. It's a non-trivial interactive proof. Yes, also I am recording right now. There's a question. I have already started recording, so sorry, I should have said that. And again, I'm clipping the beginning and the end, so that if you want to ask questions after the recording at the end, there's a possibility. And also what we saw last time was an upper bound on the class of interactive proofs. So starting with this lecture, we'll spend a couple of lectures trying to further explore the power of interactive proofs to try to go beyond graph non-isomorphism, okay? So and specifically today, we're going to look at interactive proofs for so-called counting problems. So specifically, what are counting problems? So we'll get to that. So graph non-isomorphism is an example of a problem in the complexity class coNP that is not known to be NP. Yet, at the same time, graph non-isomorphism is not believed to be coNP complete. So it's not that, oh, we have an interactive proof for GNI, now we have the entire complexity class coNP done. That's not true. Or at least we don't believe it's true, because if GNI were coNP complete, then there is some complexity result that says something really weird happens, like the polynomial hierarchy collapses to the second level. So we don't expect to have interactive proofs for all of coNP by just proving that GNI has an interactive proof. So we're going to need separately a theorem. And what we're going to see today is an interactive proof for the canonical coNP complete problem, unsat. Those are Boolean formulas that are unsatisfiable. So this is the analog of how, for the complexity class NP, the problem sat is NP complete. Okay, so rather than asking, is a formula satisfiable, namely, does there exist an assignment that makes the formula happy, return true, here we're asking, is it the case that every single assignment makes the formula return false? Okay, that problem is coNP complete, and we'll show an interactive proof for it, so that it will tell us that the complexity class coNP is contained in a complexity class IP. All right, and then we'll see how, with basically minimal extra effort, we'll show that another problem related to satisfiability called sharp sat. What is sharp sat? It says, here's a formula and here's a positive integer, except if this positive integer is precise, or here's a non-negative integer, except if this non-negative integer is exactly the number of satisfying assignments of the formula. So the problem is to count the number of assignments. Notice that this problem is strictly harder than both SAT and unsat, right? Because unsat is when this number is 0, sat is when this number is positive. Here we want to know what is the exact number, okay? Once you have an interactive proof for sharp sat, then we get a containment of the complexity class p to the sharp p. Let me just remind you, this is it's basically the complexity class that you get when you take a polynomial time machine and you let the polynomial time machine or algorithm solve sharp sat problems for free, okay? Now, these are called counting problems because it's basically like a polynomial time computation that involves solving very hard counting problems whenever it wants, okay? All right, so that's what we're going to see today. And first I want to claim these two results should be surprising. First and foremost, depending upon with your familiarity with complexity theory, these results are like many, many more languages beyond NP. So here's like a diagram of here you have the usual complexity class P. Here's the complexity class NP. Last time we saw GNI, which is believed to be somewhere here, okay? The first theorem tells us that all of coNP have interactive proofs, but then the complexity class P to the sharp P is actually enormous, okay? Like, you should kind of read up on it offline to like appreciate how huge it is. So you can actually generalize the notion of NP and coNP into something called the polynomial hierarchy. These are basically alternating quantifiers on Boolean formulas. So here is exists, here is for all, here is exists for all there exists, and so on and so forth for any constant number of alternations. P to the sharp P contains all of that, okay? So this hierarchy is also believed to be strict, namely goes on forever. And after this forever, there is P to the sharp P. So this is really like an enormous number of languages, and we're going to have an interactive proof that lets us support all of them. Another thing that should be surprising about these theorems is that kind of the intuition for the interactive proof for GNI from last time made some pretty explicit use of like special properties of graph isomorphisms, that if you take a random permutation and apply it to a graph, then you're fully randomizing a graph within its equivalence class, okay? Now, it's kind of unclear, with a Boolean formula, like, what are you going to do? Are you going to try to apply some similar ideas and try to re-randomize the formula and try to hide it within other formulas? It's kind of unclear what we're going to do. And that's precisely why to prove these theorems, we're going to have to learn some new techniques, and specifically we're going to be exposed for the first time to two fundamental tools in the theory of probabilistic proofs. One is arithmetization, and the other one is the Sumcheck protocol, okay? People are trying to ask questions. You know what? It could be that I don't have my audio on. Let me just try that. Can somebody who did ask a question try again? Let me try. Okay, now I do have my audio on, but probably Zoom is thinking of a different output because I have a bunch of cables attached to my computer. Okay, try again. I know I should have the audio on.
Any luck? Can you hear me?
Yes. Sorry about that.
Okay. Yeah, sorry, this is Chinmay. So why are you going through these middle proofs when you could just start with something like P spaces contained in IP? Are these constant round proofs? This coNP and counting one, are they constant round or?
The question is, why are we sort of looking at these theorems rather than just jumping all the way to the inclusion P spaces contained in IP? The reason is that so that's the subject of the next lecture, and that the protocol that shows that P space is contained in IP makes use of both arithmetization in a different form for a more complicated setting, and also doesn't use the Sumcheck protocol, or rather it uses a variation of the Sumcheck protocol, but the Sumcheck protocol on its own will be used later in this course elsewhere. Also, honestly, like the inclusion P spaces contained in IP is strictly more difficult than whatever we're doing in this class, so I view this as a useful stepping stone. In terms of round complexity, both the proof that coNP is contained in IP and P to the sharp P is contained in IP, they do not have a constant number of rounds. In fact, there is complexity theoretic evidence that I can link later in Piazza that show that we do not expect, even for coNP, to have not even constant, a polylogarithmic number of rounds. And instead we'll have to be content for now with a linear number of rounds, just like for p-space.
Okay, perfect, thanks.
Yeah. All right, anybody else was trying to ask a question while I didn't have output? Okay, great. So that's the plan for today. Okay, and this I have on some out of order animation. So let's first look at arithmetization. So we're going to be working with Boolean formulas. So let me remind you what is a Boolean formula. A Boolean formula is a tree, okay, that kind of looks like this. That's a tree, where every leaf node is labeled by a variable. So for example, here, this leaf node is labeled by x1, this one by x3, this one by x2, this one again by x3. And every internal node is a logical operator on its children. So here, for example, you have the OR of x1 and x3. Here you have a NOT of x3. Here you have the AND of the output of this gate and x2. And this is the output of the formula, right, at the root. Arithmetization is an informal term for a set of techniques. And here we're going to see a particular instantiation of arithmetization that replaces each logical operator with an arithmetic operator. So here we're going to replace not x with 1 minus x and y with x times y, x or y with x plus y. All right? Now when you do that, just syntactically, you're going to just get another tree where, guess what? All the nodes have just been relabeled precisely as I have indicated. Okay? So I see that in my feed there's a lot of lag, but I'm not sure if you see it as well. All right. So in this way, we get a Boolean formula as input, and we're mapping it to a polynomial. Okay? And this polynomial has several properties. The first one is that the degree is bounded by the size of the formula. What's the size of the formula? It's just the number of nodes in the tree. And moreover, just like I could evaluate the formula efficiently, I can evaluate this polynomial efficiently in time, number of operations that is proportional to the size of the formula. So, why are we doing this transformation? Well, here's a claim that if the formula is unsatisfiable, okay, so there is no assignment of the inputs to the formula to make it true, then we actually get the fact that the sum, in fact, when you evaluate this polynomial at every input, you get 0. In particular, the sum gets 0. Why is that? Well, let's see, for instance. Here, if not x was going to be 0, that means that x was going to be 1. But 1 minus x is 0, right? So again, this preserves the zeroness of the input. If x and y is 0, it means one of the two is the 0, right? Maybe both. But either way, x times y is going to be 0. If x or y is 0, it means both of them are 0. And so again, x plus y is 0. So even though we may be, let's say, think about it for now working over the integers, a polynomial over the integers, just evaluating the polynomial at any Boolean input, if that input made the formula false, then the polynomial will output 0. In particular, so is the sum. However, if the formula is satisfiable, then there's going to be some input somewhere that makes the formula be positive, okay? For example, here, if both x and y is 1, then x times y still is 1. If x or y, one of them is 1, then this is going to be evaluated to 1 or 2, right? Now, as you go through this formula, you might just move away from Boolean outputs, but you're going to go to some positive integer, okay? So I know definitely that the sum is going to be positive. Now, this sum cannot be too large either. For example, let's just, for simplicity, we assume that the formula is in 3CNF form. That means that the formula comes in an end of clauses, each of them with 3 letters with ORs, okay? Then the size of this integer can be at most 2 to the n times 3 to the m. Why? Because the sum has 2 to the n terms, right? So that's just the sum. And each term will have size at most 3 to the m. Why? Because each clause, in the worst case, is going to become 1 plus 1 plus 1, so that's 3. And I have m clauses, so it's 3 times 3 times 3, m times, so it's 3 to the m. And in worst case, every single assignment makes the formula satisfied, so this sum will be of size at most 2 to the n times 3 to the m. So why do we bother about this? Well, because now we can switch over and start working over fields, which are much nicest to work over, and turn this into not just a positivity condition, but some equality condition. If I start working over a field, a prime field where the prime is large enough, so larger than 2 to the n times 3 to the m, the largest that this could ever be, then I have encoded the unsatisfiability of the formula into the zeroness of this sum, right, over this field. All right? So in sum, we started with a problem about Boolean logic, and we ended up with an arithmetic condition about a low-degree polynomial that we can evaluate at any location efficiently. Okay? So are there any questions about this? Now, I'm kind of saying in a matter-of-fact way, but actually arithmetization plays a very deep role in complexity theory. For example, it's a technique that we say is non-relativizing, okay? In a sense that it is a type of thing that you can do when you actually get to see what the formula is like, rather than having black box access to the formula, for instance, okay? And because it's non-relativizing, then sort of it is a so-called essentially different technique than many other sort of techniques in complexity theory. Here it looks pretty mundane. We're just kind of replacing operators and kind of converting stuff. But is it at least syntactically clear what's happening and why we have this punchline that like we've encoded the unsatisfiability of a formula into a sum, basically a Sumcheck problem, and to check the sum of some polynomial.
If you take the formula not x or y, where x or y is in parentheses, then wouldn't that evaluate to a negative number when x and y are both true?
Not x or y. It
would be 1 minus 2, which is negative 1.
Oh, you're saying yeah, I should probably, okay, good point. Let's, I really should push the knots all the way down. And you can do that using De Morgan formulas without blowing up it's a good catch. I should go and fix the slides. Let's just say that we've pushed the knots all the way down and we're working with a 3CNF. In that case, the knots will appear only at the bottom of the tree and you will have no negative things. So it's a very good catch. So for a 3CNF, basically, the knot will appear right away. So that is either 0 or 1 and it's preserved. And then the positive integers only appear at the second layer where the knots are not there anymore. We'll see later a different arithmetization that is slightly more precise and we don't even have to worry about that. But this particular one, I think you need the knots at the bottom, and one way to ensure that is to work in 3CNF. Very good catch.
Hi, Alessandro.
Yeah.
So you have written that degree of P is less than the size of the formula. Isn't it exactly equal to the depth of the formula?
Depth, it could be the size, right? Sorry?
So when you represent this formula in a tree format, so the degree of the polynomial that you form out of it will exactly be equal to the depth of the
I don't think so, right? Because if you have an end here, right, you have degree contributions from the left and from the right, right? So it still goes up the degree, even though the depth didn't really, so it doesn't go up by 1. You have to sum the contributions from the left and the right because there's an end, right? So every time you have an end that joins two trees, you get the sum of their degrees because you're multiplying everything.
Right. Okay. Yeah.
But yeah, good question. There's another question. This works for any Boolean formulas, not necessarily 0-1 output, using Fourier expansion. Boolean formulas have 0-1 output, no? Also, if you start talking about Fourier expansions, we start working over the reals. I want to try to keep inside the sort of finite fields rather than infinite fields. So maybe you can ask me like after class about this question about the Fourier expansion. All right, so this is arithmetization. Now, a priori, sort of reducing your question about Boolean logic to something looks like this. It's like, okay, well, so what? I can reduce my problem to a bunch of other funny-looking ones. But something interesting that happens in probabilistic proofs is that we have very powerful interactive proofs for solving problems of this sort. So a lot of basically the design principles of probabilistic proofs is take your problem and rewrite it in something about a sum over hypercube. That's like a very common design principle. And here we are indeed following that. And wait, how did it go away? It just crashed maybe? All right. So now I'm going to present a protocol for solving Sumcheck problems. So statements of this sort, you have a sum of some polynomial. Before we were looking at the sum over all, basically the Boolean hypercube. Here we're just going to look at some generic hypercube. So I'm summing over all dimensions of some h to the n hypercube. For example, when h is 0 to the 1, it was the prior case. And instead of just checking that the output is 0, we'll check that it is some value. Okay, and we're working over some generic finite field here. And we want to construct an interactive proof for this problem. Now, the polynomial itself, for now, I'm just going to think about it that the verifier has oracle access to it. Later on, when we'll use it, the verifier really will have an arithmetic circuit to evaluate the polynomial, because maybe the polynomial itself is too large to represent kind of as a list of monomials. The prover has explicit input to the polynomial. And so let's talk about the Sumcheck protocol. It's a really cool protocol. It's I can't just incredibly versatile tool that it will kind of come back several times this semester as a foundational tool, both for theory and then in the real world it's also used. So how do you solve this problem? So notice that we have a dimension here that if the dimension was small, we could probably solve this problem easily. So the idea of the Sumcheck protocol is to reduce the dimension one at a time. Okay. Specifically, we're going to try to peel off one variable and just kind of try to reduce it to a similar statement about the same problem. So in the first round, the prover computes a univariate polynomial that basically says, okay, I'm just going to take the sum over all variables but the first one. So I'm just going to leave that free. Okay, and this is going to lead to a univariate polynomial. Okay, now because I know that p has small degree, small total degree, that's what we saw in the prior slide, then this univariate polynomial will have small degree, right? Because that's just the degree in the first variable. And what the prover is going to do is just going to send it over, right? This is okay to send it, it's not too large, okay? It's a univariate polynomial of small degree, polynomial degree. And from the verifier's perspective, it sees the prover sending some univariate polynomial that claims to be this entire sum, but with the first variable left free. So the first thing the verifier should do is to say, okay, let's just check that. It's going to check that if I sum over the variable left free, I really do get the sum that was claimed. Okay? Now the verifier is going to sample a random field element and send it over to the prover. And the prover will kind of fix this first variable at the randomness sent by the verifier and sum over everything but the second variable. So this leads again to another univariate polynomial. Okay? The prover is going to send it, and this time, again, like from the perspective of the verifier, the prover is sending some univariate polynomial that claims to be the original polynomial with the first variable fixed at W1, right? And really, in the honest case, that really was P1. If P1 was the sum of everything but the first variable, then I can just plug in W1 and check whether summing this over the second polynomial, which should have left its second variable free, I get these two polynomials to agree. Okay? And we continue in this fashion, okay? Until in the last round, the we have fixed all but the last variable. This leads to, again, a low-degree univariate polynomial, which the prover will send over. The verifier will again check that it matches the previous polynomial at that random point, and we will pick a final random field element to send over. Now, the prover is not going to do anything with that, so this is more like a formally sending, doesn't really send it. And then there's a final claim that says, look, if really the last polynomial was the original polynomial with all but the last variable fixed, let's finally go ahead and check that. Notice that I, on purpose, used blue for denoting the original polynomial, and notice that the verifier never touched the original polynomial but for this last check. This is where kind of it anchors to, you know, the object about which we're discussing. Okay? Here it is checking whether indeed P at the locations W1, W2, and so on and so forth, it equals the last polynomial at Wn. Notice that each of these polynomials was sent before that point was sampled. Okay? So P1 was sent before omega 1 was sent, W1 was sent to the prover. Okay? This will come back later. Okay, so this is the protocol. We'll analyze it shortly. First, I want to remark some things about computational efficiency. Solving this problem would require evaluating P h to the n times. If h, for example, is size 2, that's 2 to the n times. That's a large number of places. Yet, the communication complexity of this protocol is just n low-degree polynomials, okay? Remember that P in the prior slide had a polynomial degree. So this entire thing is a transcript that involves a polynomial number of elements, okay? Much less than exponential number of locations, which is h to the n, right? Now, the work of the verifier is also small, right? It is doing n sums, right? 1, 2, up to n, right? Each sum involves summing the polynomial h over h elements and evaluating it over each of these, okay? So you're summing it over h locations, and each evaluation will cost you the degree of the polynomial, okay? So again, this is exponentially less than h to the n. It is like n times h, right? And then times some, you know, polynomial blow up by the degree. And of course, in the end, we need one evaluation of the original polynomial p, okay? So is it clear that at least from a computational efficiency perspective, the verifier is doing much less work than solving the problem by itself? Again, the difference is
yes.
h to the n versus...
Question.
Yeah, go ahead.
What is this deg in? Is it in there? Degree in, or what's the notation?
Sorry, like I should have said it more explicitly because it didn't... So I have a... when I am annotating the slides, there is a super annoying like toolbar that appears like at the bottom of the slide, and it's exactly above deg in. Okay, so now that I can see it again. So notice that obviously the degree of the original polynomial is going to influence the degree of the univariate polynomials I send, right? Now, we have a bound on the total degree of P from the prior slide. Though really, what matters most of all here is the individual degree, okay? So when you have a multivariate polynomial, you can bound the total degree, which is the sum of the powers over any monomial, right? The individual degree is the maximum of the powers over any monomial, okay? Obviously, a bound on a total degree implies a bound on the individual degree, right? Because it cannot be greater than that. And here I'm just remarking that even if we only had a bound on the individual degree, we would still be fine, though actually we do have a bound on the total degree. They're not far off from each other anyways, because there's only n variables, so they can only be n times away from one another. Here I was just trying to say that the individual degree is the one that really matters. But again,
so
yeah.
For Boolean circuits, deg int of p would be 1?
No, it would be some...
No.
No, it would be some polynomial, right? So we can go back to the prior slide. Here, for instance, the variable x3, let's suppose that here variable x3 appears here and here, right? So as it travels up here, you will have x3 appearing here and x3 appearing here, so we'll have x3 with degree 2, right?
So is it related to the depth of the circuit? Or more than that, like before?
The size, really the size, right? So it could be that the entire, it could be that x3 is extremely popular and appears through half of the leaves of the formula, and then there's a lot of n's everywhere, and so it could be that x3 appears with a power that is as high as the size of the formula over 2 or something, right? So it could be linear in the formula. And of course, the formula cannot be too large because that's the object that we were discussing to begin with, that's of polynomial size. Good question. This is more like about things when you start coding things up, from a total degree, individual degree are kind of a factor of n away from one another, so it's mostly about kind of careful bookkeeping.
I had a question.
Yeah.
So what did the prover do in the first step to make it a univariate polynomial?
It just, you sum away all the variables, right? So if p has n variables and I sum away n minus 1 of them, then I'm left with only one variable free.
Okay, yeah, thanks.
I have a question.
Yeah.
Why does the verifier send the last challenge element?
For symmetry. It could just keep it for itself, right? So it's just easy to think about it as n complete rounds, right? Where the prover moves first and the verifier replies. It's there just for symmetry. But the prover, is already done. Cool. All right, so I'm not going to go through carefully the completeness of this protocol. I'll just mention, again, the intuition is that we're just peeling off one variable at a time, and each time you just need to hook back. This is like the natural check as suggested by this strategy, okay? In the notes that I'll post, hopefully this week, there is a sort of more careful discussion of the completeness, but hopefully is at least the intuition of this protocol reasonably clear, because I want to kind of focus on the soundness right now. But
hi, Alessandro, one question.
Yeah.
So in the last part of the verifier, how is he getting the blue P polynomial? So on the left-hand side of the equation, you have to, how is he getting?
Well, the question is, how is the verifier getting it? Well, because up here, I earlier said that the verifier gets oracle access to the polynomial P. So it just sends a query to P and it gets back the answer. Okay. And the main reason why I treat it as an oracle is because, well, in many applications, like Sumcheck is a subroutine to some other things, so you don't literally have P, you just have like some representation of P instead. And in our application, P is eventually going to be an arithmetic circuit for a polynomial that has an exponential number of monomials, but you have an implicit representation for it, right? So here I want to kind of ignore that. I don't want to talk about literally giving you P, you just have oracle access to it, because anyways, that's all you need, right? You just need one query to P at a random point, and that's it.
I see. So are we assuming that this oracle is honest, like it gives honest replies back to the...
The question is, are we assuming the oracle is honest? Yeah, oracles are honest, come on. That's, So that's why you go and ask them questions, right?
Yeah, I was just thinking if we were to remove this oracle assumption, then how are we going to do it?
So you can also think of Sumcheck as a reduction, right? Instead of checking the statement, you can just output whether, you output a new claim that says, P at this location should equal this thing. And you can analyze the Sumcheck protocol as a reduction, and then V doesn't really need to doesn't really need to even touch P. But right now, I really want to give the P that we're proving things about to it, just because it's simpler to think about. We'll see Sumcheck used as a reduction in 3 lectures, I think. All right, good questions. Let's move on. So now I want to look at the soundness of the Sumcheck protocol. And the main claim is going to be that if the statement that we're proving is false, namely if you sum the polynomial over h to the n and you do not get the claimed sum that I called gamma, then the probability the verifier accepts is small. What does small mean? It means that you're going to pay n, the number of variables, times the individual degree of the polynomial divided by the field size. Okay? And as long as you make the field size large enough, I don't know, n squared or n to the 10 or something reasonable, this is going to be like, pretty small. In particular, less than half.
Is the intuition for this that you're doing n different short stipple tests and each test has probability deg of p divided by the field size?
That is intuition, and that's what we're going to talk about now. Yeah. In fact, we're going to look at it rather carefully because, throughout this course, we will not maybe go as carefully through soundness analysis as in the beginning, but it's important in the beginning to go through it carefully. That's kind of exactly what we're going to do now. By the way, I'll probably give an exercise that this boundary is actually not tight. You can improve it to this other expression that is always less than 1. This one, there are some settings that is less than 1, but this one is always less than 1, as long as you have some distance in your, but I'll give it as an exercise. All right, so let's try to, this is the first basically non-trivial soundness analysis on an interactive proof we do, so let's try to do it carefully. So first we have to fix a malicious prover, right? What does fix a malicious prover mean? In this case, the prover moves n times, okay? So it means that there are n univariate polynomials that we have to talk about. I'll call them p1 tilde through pn tilde. Now, as we go through the protocol, later polynomials can arbitrarily depend on earlier randomness. In particular, pi tilde can depend on the verifier messages w1 through wi-1. So really, these are polynomials that are chosen as functions of the randomness seen so far, okay? Now, we're going to define two events, okay? Or rather, n plus 1 events. First, I have n events that basically ask whether the polynomial sent in the ith round happens to equal to the polynomial that the honest prover would have sent. Notice that the honest prover strategy is defined even in the soundness case, because even if the sum is wrong, you can still talk about the honest polynomials that you would have sent. They are the partial sums prescribed by the honest prover, to the honest prover. So I can just consider the event. Is it the case that the ith polynomial sent by the malicious prover happens to be what an honest prover would have sent? Okay? And then I look at some other event that is, the verifier accepts. All right? So we're going to prove a lemma, okay, by induction. Let me go through the lemma and first show you that this lemma suffices to conclude the proof. And then we're going to prove this lemma. Now the lemma says the following. Give me some a variable j, starting from n-1 up to 1, okay? Then the probability that the verifier accepts is at most some expression that is reminiscent of the one that we are looking for. In particular, when j equals 1, it looks very much like it. Plus the probability that the verifier wins given that the malicious prover behaves honestly for the remaining n minus j rounds, okay, for round ej plus 1 up to en, okay? So this is just a technical lemma. We'll prove it in a moment. Why does this suffice to prove the claim? Well, let's set j equals 1 in this expression. What we get is this expression, right? When I set j equals 1, this goes away. And here I have the probability that the verifier accepts given that the malicious prover actually decided to act honestly at every round. Okay, but I want to claim that this probability is actually 0. Why is that? Well, certainly this probability is at most the probability that the malicious prover behaves honestly just in the first round. But let's look, what does it mean that the malicious prover acts honestly in the first round? It means that when it sent me p1 tilde, he actually literally sent me the honest p1 tilde, p1, okay? So it means that the sum of p1 tilde is the sum of p1, but remember, we have a false statement. If I literally sum over the first n-1 variables and then I sum over the last one, then I'm now going to get gamma because that's our assumption, okay? So the probability the verifier accepts is 0 because this is one of the checks the verifier is going to do. It's a check in the first round, Okay? Are we clear so far? Okay, nothing really has happened so far. We just set up the proof by saying here are the events, here's our technical lemma that will be the heart of the proof, and this technical lemma suffices because when you set j equals 1, this term just goes away, simply because if you act honestly in the first round, you're just shooting yourself in the foot as a malicious prover.
Can I ask a question?
Yes.
So in the definition, you mentioned that there are like p tilde 1 to p tilde, and then they are fixed. So can't the prover actually come up with the polynomials like adaptively, like by seeing like half of the wi's, then it changes its mind and changes to pick a different
yeah, it sure can. So the question was, can't the prover choose polynomials adaptively? Yes, I mean that's kind of exactly what we said here, and we must take that into account when we prove this technical lemma. But it doesn't come up yet when we use the technical lemma to prove the claim, because here all we're saying is, if when you set j equals 1, you have this leftover term. This leftover term is at most the probability that the verifier accepts and the prover acts honestly in the first round. But remember, in the first round, there's no randomness anywhere. Okay, like the prover, let's just go back to the prior slide. Here, that's the first round. There's no randomness has happened so far. And the first check the verifier does, it says, okay, if you really claim that whatever you're sending me is the whole sum but for the first variable, let me sum over the first variable and see if I really do get gamma, okay? And if the malicious prover did act honestly in the first round, that means he really sent me P1. Like his P1 tilde really is P1. But remember, the sum of P1 is not gamma because that's our assumption. And P1, by definition, is P summing variables 2 through n, okay? So we haven't yet had to deal with randomness. We're basically discussing really lousy provers. Okay, so now, we can forget about the claim, okay? And we just focus on the technical lemma, okay? This is where we're gonna have to sort of say something useful, okay? All right, so I have just copied the technical lemma here, so it's like literally a copy. First, we're going to prove it by induction on j. Okay, so the base case is when j equals n. Okay, so in this case, when we set j equals n here, or rather, we want to prove this when j equals n. Okay, let's see. Look, the probability that the verifier wins is certainly at most the probability the verifier wins, or rather the prover wins. The probability that the verifier is convinced is certainly at most the probability that the verifier is convinced, given that in the last round, either the prover did not send the correct polynomial or did send the honest polynomial. Okay? Now, I want to argue that, so we don't have to worry about the second term because that's exactly what we should be getting up here. Really, what we need to convince ourselves that this first term is bounded from above by this term over here, the individual degree of p, which is really the degree of the univariate polynomial, over the size of f. So let's look at that. So I'm just kind of expanding what this means. This is just the probability of v accepts, given that in the last round, the prover decided to send pn tilde that is not the same as the polynomial pn that the honest prover would have sent. Now, the verifier accepts if all of its checks pass, but one of the checks it's doing is this one, okay? It checks at the end of the protocol whether pn tilde at omega n really is the original polynomial p, w1, w2, evaluated at w1 through wn, okay? So this is just one of the checks the verifier does, so it must pass. All right, but notice that by definition, this polynomial p, in the end, equals the honest polynomial for the nth round evaluated at omega n, right? Because the honest prover would have sent pn, which is plugging in omega 1, omega 2 up to omega n, right? Leaving the last variable free, and then we are plugging in omega n, because these two are the same. But now look, we're saying, give me two polynomials, that are distinct. Now, Pn tilde may depend on omega 1, omega 2, up to omega n minus 1, but cannot depend on omega n. Okay? Because omega n was sent after Pn tilde. Okay? So omega n didn't even exist when the prover decided to send Pn tilde. So now we have this type of statement that we'll see like a million times in this course. And I'm going to claim it is bounded from above by that one. This is something called the Schwarz-Zippel lemma. More recently, there's some trends to rename it the polynomial identity lemma because it's not just due to Schwarz and Zippel, it's due to 7-8 authors over the past 100 years. It was rediscovered many times. So in this class, we'll primarily call it polynomial identity lemma. And basically, and in the univariate case, it's a very simple, so for now we just need it in the univariate case. It just says that, look, the probability that if you pick a random point from a set and evaluate a polynomial and evaluate it at it, then the probability that it vanishes is bounded by the degree over the size of the set. Why? Because it's just saying that a univariate polynomial over a finite field has at most a number of roots that equals its degree. Okay, so it just cannot disappear in too many places. So if you pick a random place to evaluate it at, then look, in the worst case, all the roots of the polynomial are inside S, and here are so many, right? So there just cannot be too many anyways. In this case, we're looking at the quality between two polynomials, but it's the same thing, right? I can just move this on the other side, and I'm looking at the difference I'm asking, when is the difference of these two polynomials vanish at omega n, okay? Well, that's bounded by the degree of the difference, which is at most the maximum of either polynomial, and really that's the individual degree of P, okay? So here we have applied, this polynomial identity lemma. All right? So nothing much has happened, okay? All we're saying is that if in the last round the prover is stupid enough to send the wrong polynomial, we'll just catch it because we're comparing against the truth of P, okay? All right. All right. Now in the inductive case, we're going to say, okay, let's assume that the lemma holds for j equals n, I minus 1, blah, blah, up to 2. We want to prove it for j minus 1, okay? So, all right, here is just the inductive assumption, okay? So we're applying the assumption for j, okay? And I can say, look, let's break up this probability and say, yeah, okay, so if we want to understand what is the probability that the verifier is convinced and the prover decided to be honest starting from round j included and onwards, well, that is at most the probability that he decided to be honest already in round g minus 1, or he started deviating in round g minus 1, given, but also that he was honest later on, okay? Because if he was honest, if he decided to be dishonest later, we're going to be already fine, like we already took care of it somewhere else, okay? So here, this part here, we are fine to keep around because that is the statement for j minus 1. Really, we want to convince ourselves that this is the case, but that's, again, an application of a polynomial identity lemma. Why? Because we have a check, which I didn't write down in the slides, that p j minus 1 evaluated at omega j minus 1 is, let me go back here. There we go. We have a check like this one that says, if you send me this polynomial, this was pj minus 1 tilde, and I sum it up, right? And it is different from and when I sum it up, it is a different polynomial than from the honest one, okay? Now I'm going to be comparing different polynomials here, okay? So, okay, I didn't really have much space to kind of work it out here because, okay, it requires another half slide. But again, it will be done carefully in the notes, but it is, for now, just another application of the polynomial identity lemma, okay? Basically, you have a similar derivation as this one where you say, okay, that means that a pj minus 1 tilde was not equal to pj minus 1, but let's look at the test we really are doing, and then it will become basically a statement about comparing pj minus 1 tilde and pj minus 1, okay? The honest one. So if we take that into account, then we kind of bring it in here and we have proved the statement also for j minus 1, all right? So hopefully that makes sense. And we have, as Aline was saying earlier, we have applied the polynomial identity lemma n times in the base case and in the remaining n-1 cases. So in the end, we have n times this contribution, right? Right. Questions about this? Okay, so I'll have various exercises that are about basically proving variations of the Sumcheck protocol that you can use to kind of familiarize yourself with this type of proof, okay? This type of proof, it's useful to kind of do it once and then kind of you don't have to do it again, and it's like good intuition that stays in your head, okay? All right, so if there aren't other questions for now, I don't see them in chat and I didn't hear them. So we're gonna move on. So let me kind of step back for a moment. So we just analyzed the Sumcheck protocol, and here it is. And the Sumcheck protocol was an interactive proof for statements of this sort, okay? But remember, like we arrived at statements of this sort because we were interested in other problems first and foremost. So now what I want to do is I want to come back and explain how you take the Sumcheck protocol and you augment it into an interactive proof for unsat, okay? The problem of proving that a Boolean formula is unsatisfiable, okay? So let's go there now. All right. So here's how an interactive proof looks like. Both the prover and the verifier take as input the 3CNF formula that we want to consider now, and the prover wants to convince the verifier that it is unsatisfiable. Now remember that the arithmetization required us to consider a prime field for a large enough prime. So the first message from the prover to the verifier consists of an integer, and the verifier checks that this integer is large enough and also that it's not huge, right? I mean, if the prover, sends like the entire universe, you say, no, like I'm not going to try to read the universe. I know that the prime should have been at least as large as my desk, not the universe, right? So the verifier ensures that the prover didn't try to kind of send prime that is not too large, okay? But is it even a prime? So the verifier needs to check that it is a prime. And here, it doesn't have to be a deterministic test. It can just be some probabilistic test like Miller-Rabin. You just need to get some good enough error bounds that you're happy with, okay? So now the verifier really has a prime that is large enough, but not too large. And both the prover and the verifier individually, kind of in their own, they do some local computation to arithmetize the formula over the prime field FQ, okay? So now they have an arithmetic circuit over FQ that represents the formula they started with. And okay, now we are ready to run the Sumcheck protocol. They just run the Sumcheck protocol on a statement that says, if you sum this arithmetic circuit over the Boolean hypercube, do you really get 0? Okay, and then, so this is I'm just basically kind of programming the inputs to the Sumcheck protocol here. The field is FQ, H is 0, 1, the number of variables is N, the ones of the same number of variables as the variable. The claimed sum is 0, and we're talking about P, okay? Now, notice that at some point, the Sumcheck protocol on the verifier side is gonna say, hey, I need to query P at a location, this location, okay? And but that's the Sumcheck verifier. The Sumcheck verifier is living in the head of this other verifier. So this other verifier intercepts this query and says, okay, I know how to evaluate it. I'm going to evaluate the arithmetic circuit I have for P in polyMN time. That's just basically, I evaluate the tree that represents P. I get back some answer, and I return it to the verifier of the Sumcheck protocol, and that's it. Okay. So there's a question: does the Sumcheck protocol work for a univariate polynomial, or should it be at least a bivariate polynomial? It's a good question. So the Sumcheck protocol we see here only gives you advantages when you have more than one variable. If you have two variables, it gives you like a square root advantage. If you have a polynomial number of variables, then it gives you an exponential advantage. We'll see later in the course, maybe in, 10 lectures, what you can do about Sumchecks for univariate polynomials. But for now, you really want to think of the setting that we are in this multivariate polynomials. There is h is small, like the set over which we're summing, and what's big is h to the n, okay? In this case, we have 2 to the n is big, right? It's all possible assignments. And but we're happy to work with multivariate polynomials, okay? There are different reasons for why Sumcheck over univariate polynomials will be useful later in this course, and you need a slightly different protocol. But yes, there are univariate Sumchecks out there. They're just different protocols. Good question. So now, this is an interactive proof for proving that a formula is unsatisfiable. Because unsat is coNP complete, then that tells us that the complexity class coNP is in IP, because you just, from whatever language you're starting with, you just reduce it using a polynomial time reduction to some corresponding unsat problem, and then you run this interactive proof. Any questions about this? We've proved the first theorem now, okay? Notice that the exponential speedup in the Sumcheck protocol is important, because here we really do have 2 to the n possible assignments, because the verifier doesn't have to sum up or consider all these 2 to the n possibilities, but is running the Sumcheck protocol, then it is still running in polynomial time. All right, so I don't see other questions for now, so let's continue. So we had another theorem we wanted to prove, which was we wanted to also handle the sharp sat problem. Namely, proving that a Boolean formula has a specific number of satisfying assignments. I don't know, like 35, okay? Out of 2 to the n. So for that, we're gonna need to change a little bit the arithmetization, because the one that we had was rather coarse. Namely, for every assignment, if the formula was false, then we knew that the polynomial would output 0. But if the formula was true, all we knew really was that the polynomial would output some integer that is greater than 0 and at most 3 to the n. But yeah, it's not very precise, right? What integer is it, right? So if we were to sum this up over the entire Boolean hypercube, we just get some unpredictable sum. Okay, so we're gonna get some more control here, and it's actually pretty straightforward to do that. We're gonna just tweak the arithmetization ever so slightly. We're gonna change the OR operation to be more precise, to basically always preserve Booleanity. So here the problem was that if x and y are both 1, then here we would get 2, right? But in that case, we could just subtract 1. Okay, this is basically an arithmetization of a NAND, of like you write x or y through NANDs, and then you kind of use the other things here. But this one basically, for every Boolean input, it just exactly preserves it. Okay, so that should be like easy to see. And now the new arithmetization has this very precise behavior that for every Boolean assignment to the formula, if the formula is false, we get 0. And if the formula is true, then we get 1. Because each of these teeny tiny gadgets always preserve the Booleanity of their inputs, okay? 0 goes to 1, 1 goes to 0. Here, the truth table of the AND is preserved exactly by x times y, right? And the truth table of x or y is preserved exactly by this arithmetic expression, okay? So as long as we always have Boolean inputs, we will have Boolean outputs. And so therefore we have this is the case. Now that we have this arithmetization that is like more precise, it's immediate to see how to reduce sharpsat to a sumcheck problem. We pick a prime that is larger than 2 to the n, and then the statement that the number of satisfying assignments of the formula is c is, according to this new arithmetization, precisely the sumcheck statement, checking whether the sum of p over the Boolean hypercube is exactly c modulo q. Okay? Why? Because we have exact control over what happens at every location of the Boolean hypercube. Okay? So, is there a question? Why did we even use the original arithmetization? It seems like a simple improvement. Are there any downsides using for this unsat? So, notice, to a first approximation, this is just a better arithmetization, okay? The previous one was just to kind of, you need to get attuned to the fact that there exist different arithmetizations. We'll be using all kinds of different ones in this course, and you need to not just take it off the shelf, not looking at it and just apply it. You need to kind of know how it behaves. So this is, trying to remind you within a lecture that there are different types of arithmetization. Now this arithmetization has maybe a minor disadvantage, which is now x or y actually increases the degree also, whereas before it didn't. Before it was just x plus y. So if you had a formula that was full of ors, okay, then your degree wouldn't increase as much. Okay, now it increases a little bit more, but it's okay. Like we don't care. It's still like a polynomial degree. So to a first approximation, this is just a better arithmetization. But the reason why it's there as a stepping stone is for pedagogical reasons. And generally there's a comment there that says different arithmetizations for different problems, and both in research and in the real world, when you're trying to achieve some fine-grained goal, one of the components you need to evaluate to ask yourself, am I doing the right thing? It's not just the proof system itself. Sometimes it's the arithmetization. There's just better and worse arithmetizations, and you just need to be able to kind of play with them to find the one that kind of works for your setting, okay? And there is more and arithmetizations, and they're going to look very different. And also, arithmetization is not a formal term. It's just an umbrella term to mean like a set of techniques for converting in various ways combinatorial problems into algebraic problems. And I don't really know how to define it. And all of those things are non-relativizing in a very broad sense. Okay, so now we have arithmetized the problem of counting the number of satisfying assignment for a Boolean formula. But look, we already have the sumcheck, and this problem already falls under the something that the sumcheck can handle. So we come back here and we say, all right. So if we want to design an interactive proof for this problem, then again, we ask the prover to send a prime. Now we check that it is larger than 2 to the n rather than 2 to the n times 3 to the m. We still have to check that it's prime. Now we do this slightly different arithmetization, but it's still some arithmetization. And we run the protocol where now instead of having 0 here, we put c here, right? And like before, the outer verifier will have to answer the query 2p for the inner verifier by evaluating the arithmetic circuit that I have derived. So this is an interactive proof for sharpsat, and to finish the proof that p to the sharp is an interactive proof, has an interactive proof, you need to actually go back to p to the sharp p problem, which is a machine that decides by making sharpsat oracle calls. So basically, your verifier for p to the sharp p is running this machine in its head, and every now and again the machine will say, oh, I have a sharpsat oracle call to make. Could you please ask the prover to help out? And it will say, sure, here's a formula. The prover will kind of reply and say, look, thank you for the formula. This is the number of satisfying assignments for it. And you don't have to trust me. Let's run a sum check for that. And I just do this over and over again for as many calls as the machine wants to make. Okay? And this is an interactive proof for p to the sharp p. Any questions about this? Why do we not need 3 to the m anymore over here? It's a good question. If we go back to the previous slide, because now we have this more precise arithmetization, we know that everywhere on the Boolean hypercube, we will get either 0 or 1. So the largest that this sum can be over the integers is exactly 2 to the n, achieved precisely when the formula is satisfiable by every assignment. Okay? And we don't have this kind of larger integer anymore that we need to account for. We have 1. So now it suffices for no overflow to pick q to be only larger than 2 to the n. Hopefully that answers the question. And the final interactive proof for p to the sharp p is this one. Okay? Now, there's another question that says, can 2 to the n less than poly mn be true? So, look, oh, sorry, it's a good question. That's, nobody caught it until now. There's a question that says, how the hell can you have 2 to the n less than poly mn? What I meant here was something else, sorry. It was 2 to the poly mn. Sorry, I'll fix it in the slides. What I wanted to make sure was that the representation of the prime is not too large, right? That log q is something that I can talk about, okay? So this is just like a mistake in the slides. I'll fix it before posting them, so good catch. Yeah. Hopefully that clarifies it. Okay, there are more good questions, or questions in general.
But isn't the verifier running in polynomial time? How could he ever receive such a queue?
Yeah, like it's I could also just drop this check and say, well, I prepared some location on the football field where the prover gets to write the prime, and if it takes more than a football field, I'm just not gonna look at it. So here I just wanted to highlight that, I mean, there is still somewhere some restriction that the prime cannot be too large. Otherwise, like that's not okay. You can either think about it as the channel restricts it, or the verifier refuses to talk when it gets too large, something, right?
The way I'm thinking about it is it's not an interactive proof because the verifier couldn't actually read such a large queue.
Yeah, and that's a fine way to think about it, but it's important that this subtlety is something you're aware of, which you are, and this being in the slides is to say, be aware that because it's an interactive proof, the verifier cannot talk about things that are too large. All right, now, are there more questions about this slide? Because if not, I want to go back to a prior slide to make some comments. All right, so let me do that. So the Sumcheck protocol, basically with no change, as it appears in this slide, will be used over and over in this course, okay? For a variety of things. In fact, we'll use it again, I think, in 3 lectures, okay? However, next lecture, there's going to be, so this I want to go back and maybe add some more context to Chinmay's question at the beginning of this class. Next lecture, we have something to do first, which is we want to prove that we want to finally characterize the power of interactive proofs. We want to prove that every language in p-space has an interactive proof. For that, we will not be able to use the Sumcheck protocol. But knowing about the Sumcheck protocol will help us design a different protocol. Now, that other protocol is primarily used mostly for that proof, so it will not keep showing up later in the course, yet but we'll look at it primarily because it's a good exercise. There will be like a pretty interesting arithmetization, and it's like it's a really cool protocol. But the one that you absolutely must know, both as a theoretician and as a practitioner, is this protocol here. It's just unreasonably useful. It's just not clear now why this thing that helps us with p to the sharp p has got anything to do with other things. But the Sumcheck protocol, being able to play with it, kind of invoke it in different settings, is just incredibly useful. Like, I can't sort of understate this enough. All right, so I would like to, there we go, come back to the beginning of here. So today we looked at two theorems, okay, that coNP has interactive proofs and p to the sharp p has interactive proofs. We proved both with the same paradigm, arithmetization and then Sumcheck protocol. And I just want you to remember that p to the sharp p is a lot of languages, okay?